Okay, so today we are going to discuss about the Fermi Dirac distribution function. Okay, so Fermi Dirac distribution function. Okay, so before going to in detail about this, okay, so let us consider the students can enter in the classroom, or for example if you take the any cinema hall, okay, so cinema hall or any party hall, okay, so how the students are going to accommodate in their corresponding chairs, okay, so if you consider like that it will be very easy to understand, okay. So here also if you consider the any material, or particularly if you take the crystal, so many energy bands are there, okay. So in that energy bands number of available energy states are there, okay. So for example if you consider the, so these are all energy levels, each energy levels, okay. So something like this, okay. So these are all energy levels, okay. So here, so it is very similar to our classrooms, okay. So these are all benches if you are consider, okay. So how the students are accommodated in these each benches. Similarly, how the electrons are, these are all energy levels, okay. So each energy levels, how the electrons are going to sitting or occupying these energy levels, okay. So there is a certain rules or regulations are there, okay. So for example if you take the how it is going to accommodate, okay. So distribution of electrons in these energy levels should be obeyed by the Pauli's exclusion principle, okay, since it is a fermions, okay, electrons. So according to Pauli exclusion principles, okay, so maximum 2 electrons can hold the same energy state, or in other words no 2 electron can occupy in the same quantum spin, okay. So for example if you take the opposite spin, maximum 2 electrons can hold, okay. So each energy level maximum 2 electrons, okay. For example for easy to understanding, one is up and one is down, okay, one is up and one is down like this, okay. Or in some other textbooks they will keep it as a just energy levels, 2 dots, okay. So both are same only, okay. So something like this, okay. So for example if you, easy to understand, okay. So 2 electrons, okay. So maximum filled energy, okay. So for example this is the maximum filled energy here, okay. So this is the maximum filled energy level, it is called Fermi level, and the energy of this electron is a Fermi energy, okay. So EF0. So similarly here also this is a EF, okay. So for example below EF, okay, so here if you take, okay, so these are all, so these are all completely filled, okay. So these are all lower energy levels, or completely occupied electron, okay. So these are all completely filled, okay. So whereas here these are all upper energy levels, okay. So here all are completely filled, means it is a some percentage of the probability are there for electrons to identifying or occupying, okay. Whereas here in the above EF state there is no electron we cannot see, okay. So which means occupation of electron in the higher upper energy state it is a 0, which means it is a 0 probability to identifying the electron, okay. So it's very similar to in our class, okay. So for example 10 benches are, I mean 10 rows are there, 5 rows or 6 rows are students are filled means remaining the top portion of the 4 benches, okay. So that is empty, whereas in the lower energy state or below 5th row is completely filled, okay. So that's, so energy this Fermi energy is the reference, okay. So reference energy state to identifying the whether it is electrons are occupying or not occupying, okay. So this is a reference state, okay. So now we are going to discuss these all, okay. So probability of occupying electrons in an energy levels, okay, it is based upon the certain function, okay. So that function which is called Fermi-Dirac distribution function, okay. So we can define as, so Fermi-Dirac distribution f of E, okay. So f of E is equal to 1 by 1 plus e power E minus EF over KBT. KBT, or in some textbook they may follow the KT, okay. So both are same only, okay. So this is the equation, okay. So this is a Fermi-Dirac distribution function. For example, if you keep equation 1, okay. So where E is the energy of electron, in a certain energy level, okay, in an energy level, okay. EF is the Fermi energy. Fermi energy is the highest energy, highest electron filled state at 0 Kelvin. That is very important. Whenever you are defining the Fermi energy, at 0 Kelvin is very, very important, because above the temperature, above the 0 Kelvin, it no more for the Fermi energy is constant, okay. So this is at 0 Kelvin, and whereas KBT or certain book K, okay. So it is a Boltzmann constant. And T is a absolute temperature. Okay. So based upon this function, we can easily identify whether the electrons are occupying or not in the energy levels, okay. So this is a main idea, okay. So for example, if you consider the lower the energy, okay. So here below the EF, it is a f of E is obviously it is a f of E here is 1, okay. So for example, if you consider here, okay, so f of E Fermi-Dirac distribution function is equal to 1, whereas this upper state, okay, so here f of E which is equal to 0, which means here some percentage of the probability of occupying electron in this energy level where E is less than EF, whereas here E is greater than EF, there is no more electrons are occupying, okay, which means it is a 0% of identifying the occupation of electron in an energy levels, okay. So this is a main idea, okay. So now we are going to discuss about the how with respect to temperature it is varying the Fermi-Dirac distribution function, okay. So effect of temperature on Fermi function. Okay. So first case we are going to take it out the at 0 Kelvin, okay. So case 1, at temperature 0 Kelvin, okay. So here we are going to take the for example number 1, okay. So when E is less than EF, okay, So which means it is a, so energy levels are there, Fermi energy below the Fermi energy, okay. So which means, so in this case, okay, so in this case E minus EF, which is equal to negative, okay. So now we are going to substitute in this Fermi Dirac distribution function, okay. So we know that the Fermi Dirac distribution function, okay. So f of E is equal to 1 by 1 plus e power E minus EF over kBt, okay. So E minus EF is a negative, okay. So which means 1 by 1 plus e power negative by kBt. kBt, T is at 0 Kelvin, okay. So then 0, okay. So which means it is a 1 by 1 plus 0 e power minus infinity, okay. E power minus infinity we can take it as, okay, e power minus infinity, which is equal to 1 over e power infinitive. E power infinitive is a infinitive, so infinitive. 1 by infinity we can take it as a 0, okay. So then it is a 1 by 1 plus 0, which is equal to 1, okay. So f of E is equal to 1, where when the case E less than EF, okay. So here we know that so these are all energy levels. So maximum 2 electrons can hold. Okay, so this is, for example, this is EF, which means E less than, which means here somewhere else, okay. So E somewhere else here below the energy, okay. So which means obviously finding the electron of occupation, okay. So it is 1, okay. So that's what we got, okay. So this is number 1 case, okay. So these are all lower energy, okay, lower energy state energy levels, and these are all upper energy levels, okay. So this is one, okay. So second case, if you consider, okay, so second case E greater than EF, okay. So for example, okay, so second, okay, when E greater than EF, which means we are considering this portion, okay. So in this case E minus EF, which is equal to positive, okay. So now we are going to apply the Fermi Dirac distribution function, as we know that f of E is equal to 1 over 1 plus e power E minus EF over kBt. So E minus EF is a positive, okay. So 1 by 1 plus e power positive by this kBt, T is a 0 Kelvin only, okay. So 0, so which means it is a 1 by 1 plus e power, this is a infinity, okay. So 1 plus infinity also infinity only, okay. 1 plus infinity, infinity only. So 1 by infinity is 0, okay, which means f of E is equal to 0. So which means if you consider the E greater than EF, okay, obviously identifying the electron occupation is 0, which means 0% of the electron occupancy in the E greater than EF, okay. So this is a case 2, okay. If you consider the another one case, okay, so for example, okay, so when E which is equal to EF, okay, so in this case E minus EF, which is equal to 0, so Fermi Dirac distribution function f of E equal to 1 by 1 plus e power E minus EF, okay. So E minus EF over kBt, so which is equal to 1 by 1 plus e power 0 by 0. So 0 by 0 is not no value, okay, so which means it is a indeterminate, okay, so which is f of e is equal to indeterminate, okay. So if you combine all these 3 points, okay, the case at temperature is 0 Kelvin, okay, we can draw the Fermi-Dirac distribution function versus E, okay. So for example, so if you combine together, okay, so we can draw the diagram, okay. So this is E, okay, x-axis E and this is f of E, okay. So y-axis is f of E and x-axis E, okay. So if you consider all these 3 cases, okay, so this is Fermi energy EF, okay. So if you consider okay, so this is EF, okay, so this is a maximum electron, okay, so this is 1 and this is 0, okay. So this is a some percentage of probability to identifying the electron, okay, so which means this is E less than EF, okay, whereas here in this region, okay, so which means it is a energy level lower the energy level, okay, whereas below the EF, okay, so here it is a above the EF state, okay, so in this region E is greater than EF, okay. So E greater than EF is 0 identifying, okay, so this is 1 and this is a, okay, if you find out the, here you can easy to understand, okay. So this is the 1, okay, when E less than EF, okay, so this is indeterminate and here it is a E greater than EF, okay. So this is all at temperature T is equal to 0 Kelvin, okay. Okay, so this is the case, okay. If temperature increases, okay, so little bit above, just above the 0 Kelvin, okay, so what will happen for this distribution function we will see, okay. So at temperature T greater than 0 Kelvin, okay, so which means, so E is equal to EF, okay, so in this case we can take it as f of E is equal to 1 by 1 plus e power E minus EF by kBT, which is equal to 1 by 1 plus E minus EF, okay, so E minus EF is 0, okay, so in this case E minus EF equal to 0, okay, so which means e power 0 by T is some number, okay, so some kBT, okay, so kBT, which means it is a e power 0 is 1, okay, so this is e power 0, okay, 1 by 1 plus e power 0, which is equal to 1 by 1 plus 1 is equal to 1 by 2. So f of E is equal to 1 by 2, or in other words it is a 50% to identifying the probability of electron in an energy levels, okay, 50%, okay. So when temperature increase 0 Kelvin, so Fermi energy is no more stable, okay, so it is not highest filled state, okay, so it may be filled or not filled, okay, so which means it is a average energy of the electron, okay, so to identifying the energy of the electron it is a 50%, okay, so that is the main idea. So for this, okay, so now this f of E versus E, it will be little bit shift, okay. So this is, for example, at a temperature 0 Kelvin it is a staircase type, okay, step like pattern are there, okay, whereas in the temperature at temperature T greater than 0 Kelvin, okay, so it is See, it is no more step like, it is some smooth curve it will come, okay. So for example, it is like this. So this is a 50 percentage. So something like this, okay. So something like this, okay. So this is temperature 1 and temperature 2 and temperature 3, okay. So T1, T2, T3, okay. So it is like this, okay. So which means it is a no more step like pattern, okay. So it will be changes are there, okay. So this is the main idea, okay. Step like pattern, okay. So for example, case 3, okay. So this is case 2, okay. This is case 2, temperature T greater than 0, okay. So if case 3, temperature very greater than or very high temperature, okay. So for example, case 3, when temperature is very greater than 0 Kelvin, which means EF is very greater than kBT, or in other words T towards infinity, okay. So which means all the Fermi Dirac ratio, for example, the electrons quantum mechanical behavior obviously will be destroyed, okay. So then it will be come into under the picture of classical nature, okay. So which means it is a Fermi Dirac distribution function is destroyed, okay. So no more holds good, and it will comes under the Boltzmann distribution law, okay. So quantum behavior, okay, quantum behavior to classical behavior, okay. So this is the case 3, okay. So this is the effect of temperature, okay. So why it is a important, or in other words what is the use for this means, it is a to identifying the probability of electron occupation, number 1, and Fermi energy we can easily identify, and number of free electrons over the unit volume also we can identify, okay. So these are all very important for the identifying the carrier concentration, okay. So density of state and carrier concentration, okay. So that is the important, okay. So this is the use for the Fermi Dirac distribution.